In this video, we are going to derive the period of a pendulum. So we have here a diagram of a pendulum swinging back and forth. This is the moment where it's at the apex of its swing and it is stopped to turn around and go back in the other direction. So we've drawn the forces. We have the force of tension acting along the string. We have the force of gravity acting down, and we're going to split our gravity into components, which may seem weird because a lot of what we've done so far when we've studied forces and we've studied circular motion, we've split the tension into components. But we're going to split the gravity into components, and the reasons will become obvious in a second. We're going to do a component that is tangent to the circular motion, and that component is going to cause speeding up. And we're going to do a component that is in line with the tension, and the combination of this component of gravity and tension will cause centripetal acceleration and cause it to turn. So at this point here, we know that velocity is equal to 0. And since we know velocity is equal to 0, we know that the sum of the forces, centripetal, sum of the centripetal force, which is the net force towards the center of the circle, that has to be equal to 0, because that's equal to mv squared over r. So if v is equal to 0, then the centripetal force equals 0. So that means that the sum of the forces on the ball at this moment is equal to mg sine theta. I almost ran out of room there. So this is theta here. We can see that this is theta. Those are the same angle. And then this component here could also be drawn here. You can easily see that that's mg sine theta. So we're going to use this instant to derive the equation. So we have the equation net force, so sum of the forces is equal to just mg sine theta. And I'm going to write this without vectors for right now. Now we're going to use something called the small angle approximation to derive this equation. And the small angle approximation states that when theta is less than 10 degrees or 0.17 radians, theta is about equal to sine theta. And it's actually about equal to tan theta as well. So if you do this on the calculator, if you put your calculator into radians and you do the sine of 0.17, you will see that you get a number that's within 1% of 0.17, or tangent as well. This actually works for a little bit bigger angles than 10, so you can go up to 20. 20 gives you within 2% still, and that still works out pretty well. So some people use this for 10 degrees, some people use it for 20. It doesn't really matter here. We can definitely go up to 20. So now let's look at this diagram here. Sine theta, on this triangle right here, we have this is L, and this is equal to L sine theta. So we're going to call L sine theta x. X is the displacement, the horizontal displacement of the pendulum. And since I know that sine theta is about equal to theta, then I'm going to say that theta, I guess I could just L times theta equals x. So theta equals x over L. Now I'm going to plug that into this equation up here. And I'm going to get that the sum of the forces is equal to mg times x over L. Now, if we look at this equation here, m, g, and L are all constants. Oops, that's not how you spell constants. Constants. So these are all constants, and this looks like the same model as F equals kx, where this is the constant. So here we see that net force is dependent on x, the position of the pendulum. Here, net force is dependent on x, the position of the spring. The two are related by a constant in both of the equations. So what I'm going to do is take my equation that I've already derived for the period of a mass oscillating on a spring, and all this k, the only significance of this k is that it's the constant that relates the force and the displacement. So I'm going to take this piece right here and I'm going to plug it in for k. So for a pendulum, k is equal to mg over L. And then when I do that, I get t equals 2 pi times the square root of m over, and then I'm just going to multiply by the reciprocal, so I get L and then m and g. And we can see that our masses cancel, and we get the equation t equals 2 pi times the square root of L over g, which is the equation for the period of a pendulum. Now, we noticed that when we did our lab on this, we derived this equation, and we found this using small amplitudes. If you did this lab with larger amplitudes, you would find some deviation from this equation. But for small amplitudes within 20 degrees, this works quite well.